Hey students, I got a request to make another video here, so let me give this a try. This is coming out of chapter number 36, and it's 19, so it's our geometric optics. And it looks like here we have a ball that is dropped at time equals to 0 from rest, and it's 3 meters directly above the vertex of a concave mirror. So I guess in a picture it might look something like this. Here's the concave mirror, and directly above it is the ball. And so we're going to drop it. And I guess the idea that it says it's a review problem is because, the effect of gravity. So this will take us back to Physics 121, and maybe I'll throw this equation out here that might have been a while since you've talked about it. But when you have a constant acceleration, this here mathematically describes the position, this being the initial position, initial velocity, as it comes down. So we'll come back to the review part of it, but let's just talk about the optics in general. And so this, as it says, is dropping down. Now it says the radius of curvature r is 1 meter, and that means the focal length is a half a meter. And so that's something to keep in mind here. Okay. A, describe the motion of the ball's image in the mirror, and then B, at what instant or instances, does the ball correspond? Well, let's start with A. In fact, let me take this as an opportunity. Hopefully I won't get too long-winded. But we said that this mirror, this concave mirror, and for that matter, the convex lens, are the more interesting of them because three things can happen. And so let me just put the focal point and the twice the focal point, which is for the mirror also the radius of curvature. No, that's not true for the lens, but these are important conditions here. And if we go ahead and write out the equation, 1 over p plus 1 over q equals 1 over f, we said this equation works for the mirrors and the lens as long as we obey a certain set of rules or conditions of when is p plus or minus, when is q plus or minus, when is f plus or minus. And then that, for that matter, we could have magnification and height of the image, and those could be pluses and minuses. But what we hopefully recall, and let's run through the math, is that if we have an object that is greater than 2 focal lengths, what'll end up happening is an upside down image, so a real image, will be formed that is smaller than the original object, so the magnification will be less than 1, and it'll be between this distance of f and 2f. And when this is really far away, it's a little closer in, and as it gets closer to 2f, this gets closer out, and then right there is where they transition. And so it looks like when they say what instances do the two have the, correspond, it looks like right there is certainly one of the answers. It looks like there's another one coming up here. But as then the object is now here, between the focal point and 2 focal points, the image is formed out there. Mathematically, you might say these two reversed roles, because remember, these two have to add up to be a constant for a given mirror or a given lens. So if, P is outside of 2F, then this is between F and 2F. Or the other way around, if P is between F and 2F, this then is greater than F. And that's kind of what I see here. And then another interesting one, although maybe before I leave that, I could say this was the second interesting scenario, because what we can do now is get an image, a real image, and it's bigger and upside down. And so if our object is greater than 2f, we get a real image upside down and smaller. If the object is between f and 2f, then we get an upside down image that's real, that's bigger. And then the third scenario is the one that what if the object is inside the focal point, but then we get an image looking over here somewhere, a virtual image. The light, I guess, would look something like this. The parallel one would go through the focal point. The one coming up as if from the focal point would bounce off and go straight. These two rays would have the appearance of coming from over here. And so our third possibility is that Q now is on the virtual side, so Q is now a negative number, and Q is bigger than P, which then makes the image greater than the object. So the magnification is greater than 1, and it's upright. Now, maybe all those are worth kind of seeing in more detail in terms of the mathematics here. And so the mathematics say 1 over P plus 1 over Q is equal to 1 over F. Let me write it this way. I'll go 1 over Q. This will be a 1 over F minus a 1 over a P. Maybe I'll first do a common denominator, FP. This would then be P minus an F. Maybe now I'll take the reciprocal. So Q is FP over P minus F. And maybe to help me kind of analyze it, maybe I'll do a graph. And on this graph, I will say, okay, for different values of P, so this will be my input P, what are my values of Q? And since P shows up in 2 places, that might not be a good way to write it. So let me multiply top and bottom by 1 over P so that the top no longer has a P in it, and the bottom then has a 1 minus an F over a P. And that might be a little bit nicer way to analyze this. Because looking at this, or really back here, you can see that if you start with a big P and 1 over something big, we can just say, we can ignore. Q is just equal to F. So, and I guess you see that here, a big P, F over a big number is basically 0, and you get F over 1. And so somewhere out here, maybe I'll put the value of F right here and say, all right, so when we're really far out, when P is a really big number, we get a Q that's equal to an F. But see, then notice that as P, I'll kind of imagine going in and P is getting smaller, this has to get bigger because the two together have to add up to the same number. It has to be a constant. And so what's going to happen is this is going to start arcing up. And you could even see something quite interesting is going to happen when P equals an F. So maybe I'll put an F right here. Because if P equals an F, you get 1 minus 1, and so that's an asymptote right here. And I guess technically this is an asymptote. And so we have a vertical and horizontal asymptotes here. Okay. And so I guess it's going to kind of shoot up and do something up to infinity here. And so this would kind of be my description of this, P and Q. And so again, P may start as a big number, which means Q, and then as you move closer, that's kind of how I was describing it, P starting out here with a big number, and then the Q would be right here at the focal point, and as I come in, this Q tends to get bigger, tends to move out. And so that's what I'm trying to describe. As P gets smaller, F gets bigger. Okay. Now, I commented that something magical is going to happen right here at 2f. And you can kind of see that. If p equals to a 2f here, this f over 2f is 1/2. And so you get 1 minus 1/2, which is 1/2. You move the 2 up here and you get 2f. So apparently, right at about here somewhere, which will kind of be our answer later on, when p is 2f, q calculates out to be a 2f. But maybe I won't worry too much about that because this is a continuous function. And right now, I guess I'm kind of answering this. Describe the motion of the ball's image. And so I guess I would say it's going to start at some focal length, the image is going to start at some distance away, which we probably should calculate. Maybe I'll do that now. So if I go 1 over p, so it's going to start at 3 meters, and then have a q, and I get 1 over the focal length, which is 1/2. And if I go to solve this, I guess this is a 2 minus 1/3. Oh, that's 1 over q, sorry. Let me just grab a calculator here. So 2 minus 1/3, and then taking the reciprocal of that is q equaling 0.6. Now remember the focal length is 0.5. So as we try to answer A, we might say, as I describe the motion, the image starts, so maybe I'll put 3 meters right here. And this would then start here at 0.6. Not quite at the focal point. And if I came back to a little diagram, let me do it vertical. I'll put the mirror this way. And so if the ball starts up here, the image would be beginning right there. So that's where it would look. And then as we drop the ball would be coming in, and the image would be coming out. And of course, what we're also saying here in the math is that they would be at the same point at 2f, which is 1 meter. So as the ball comes down, the image comes up. And so when maybe the image is right there, the ball will be at the same spot. And I'll just kind of draw them separately, but it would kind of look like they merge. And then as the ball passes, the image gets to bigger distances. That would be this point on the graph, whereas the p is getting smaller, the q is now getting bigger. And then, of course, this continues on until we get very, very close to the focal point. And so the ball just seems to race on out and get infinitely far away. And then as far as magnification goes, I guess it tends to get bigger and bigger also. But now the ball would transition past the focal point. And so let's come back and look at this equation when we have p a little bit less than f. Because we can't have p exactly equal to f. There's no solution. We get a 0 in the bottom. But if we take the limit as it approaches f, from the positive side, it goes to infinity. But from the negative side, it goes to negative infinity. So let me draw down here that the image would then start to appear way on this side. So as the image goes racing up to there, and kind of like a video game, if you will, goes off the top, then it reappears out at the bottom. And the negative side becomes virtual. This is back to scenario number 3. And so scenario number 3 is where now we get a virtual image. So again, the ball's kind of moving in, and until it gets all the way to 1 meter, the image only moves from a half a meter to 1 meter. Or actually technically at 0.6 to 1 meter, when this was 3 meters out to the 1 meter. But then they switched roles as the ball got closer. The image got way out there. So the image would actually be going really fast to go from 1 meter out to infinity by the time the ball goes from just 1 meter to a half a meter. And then once it crosses this point at the focal point, then it appears to be way out here at negative infinity. And then, let's look closely at this math. As p gets smaller and smaller and smaller, of course this f over p gets bigger and bigger and bigger. And it was already a little bit bigger than -1. That's here. That's why when this was just a little bit bigger than -1, we got 1 minus -1, and we were just a small number. That's why we got this negative infinity. But as it gets bigger and bigger, we can essentially begin to ignore that number 1, if you will. And this whole thing then becomes approximately f over a negative f over p, which the f's would cancel, and you just get negative p. So in this case, we have q, the image position, equaling to negative p. And that's a line, y equals negative x. So it looks like this is going to come up and eventually kind of follow a line until it hits the mirror at p equals to 0. All right, so to recap, I guess I would say this. In part A, describe the motion of the ball's image. And I would say it starts at about 0.6 above the mirror, and at first moves kind of slowly and is smaller than the size of the ball. But then, at some point, when the ball and the image are 1 meter away, we now have an image that's the same size as the ball, and from that point on, the image is now at a greater distance than the ball, and so the image goes rocketing up here as the ball falls. And it goes off to infinity. And then when the ball gets to a half a meter above the mirror's surface, it becomes at a position of negative infinity on the virtual side. And then as the ball gets closer and closer and then actually hits the surface, the image comes in and hits. And I guess if it's a ball, it probably would bounce. And so as the ball bounces up, this would now repeat. It kind of look like that ball would bounce together. And if it bounced enough to get above the focal point, then this image would go out to negative and then kind of come in again. Something like that. Bounce off. Maybe be at the same place and then fall, go out to infinity, come in from infinity. Boom, something like that. So that, I think, answers A. Describe the motion of the ball's image in the mirror. Now, the other part of this, at what instant, or instances, notice plural, do the ball and the image correspond? So coming back to my graph, they're really saying, when does P equal Q? Well, the line y equals to x, drawn a different color here, is like this. It does that. So are there any points where P equals to Q? And yes, there are. It crosses twice. And that's why they had the plural there. And this one we already talked about. It's at 2F. Let's kind of prove it mathematically. But here's another one. And that is when both P and Q equals 0. So to prove that mathematically, let me just take this equation, Q equals F over 1 minus F over P. But let me replace that with a Q, because they're saying, when does P equal Q? All right, so when are those two equal? Actually, you know what? This came from, probably, instead of undoing the math, let me just go backwards to this. So 1 over P plus 1 over Q equals 1 over F. But here I'm going to replace the Q with a P, or a P with a Q, which, well, let me just replace the Q with a P. But I'm looking, when are they equal? And the reason I said mathematically that would be nice, because we would get 2P is equal to F, and that's valid. But let me point out something. It's valid so long as P doesn't equal 0. So we have to treat that as a separate case. We have to ask ourselves, is it true when P equals to 0? Right now we have a little problem with it mathematically. But as long as P doesn't equal 0, then when we, cross multiply these, we could say this is, and there's only one solution, when P and Q are equal, when P doesn't equal 0, and that is at 2F. And so back to our graph, we could say that is one of the solutions. And so when P equals to 2F, it also equals Q. So that is definitely one solution, which we already mentioned. Now, the other solution, we got to see it in terms of a limit. We can't see it here because, like I said, this equation, because P is in the denominator, would give us all the solutions except when P equals to 0. So it kind of rules out the P equal to 0. So we still have to ask ourselves the question, does P equal to Q in the limit that it approaches 0? And so maybe, again, taking this equation, Q equaling F over 1 over F over, Q, or if you'd rather, I could do the P's. But whichever you want to look at. But let's take the limits then as Q approaches 0. And so as you heard me say earlier, we probably would do something like this. We would say, all right, in the limit, this down here gets so enormously large, we can bypass the 1. And so we can just replace it with that, which, again, the F's cancel off, and you get negative Q. Okay? And that does work when we approach 0. Does 0 equal negative 0? And yes, it does work. And so we have found up here all the times P and Q are equal when they are not 0. And then we have tested the time, are they equal at 0? And yes, they are. So I guess we have two solutions. And that's why they stated it this way. What are the instances that they have corresponding? And of course, we saw it in the graph. This line here, P equals Q, touches this graph twice. So there's two solutions because we got this discontinuity here. Now, I don't think we're quite done with the problem. Here's where the review comes in, because it says at what instances. So we are going to say when P equals Q, which say one answer is at 2F, which is the radius, which is 1 meter. So when does P equal 1 meter? And this is where we can come back to this equation here. Now, maybe we should write that equation because this is the position of it. So that X is a P. This is its original position, so that's 3 meters as described here. That is initial velocity 0, as it says, dropped. Acceleration is a negative 9.8, so with the half it makes a minus 4.9, and then t squared. And so I really want to know, so there's p equaling 1, and so this would be a 3 minus a 4.9 t squared. And so if I move the 4.9 and t squared to the other side, and the 1 and the 2, I can grab a calculator and say, all right, when does this time be equal? So 2 divided by 4.9 would be t squared, taking the square root, and it looks like at about 0.639 seconds after I dropped it, it would have fallen enough to be at that magical spot of 2 focal lengths, which is 1 meter. And so that is 1 point in time, and well as position, that p equals q. Of course, it continues to fall, and it's eventually going to hit the mirror. And so that would be then when this position is 0. And so when p equals 0, which q would also be 0, we can solve for the time. So this would be 4.9 t squared equals 3. I'm getting my calculator. I would go 3 divided by 4.9. That'd be t squared. And taking the square root, it looks like 0.782 seconds would also be a moment in time. And then not counting the bouncing, those would be the only 2 answers. All right, hope that helped.